I know we have a lot of talks going on this week, so I definitely appreciate you being here. We're very fortunate to have Professor James Long from, what, about 100 feet away or so, visiting us in the statistics department. We met James through Lucas, I guess when you arrived, you've been working on some actually astronomy-related thing, and actually some very powerful statistical analyses of astronomical data in order to derive conclusions. And so we've been since striking up conversations with Professor Long on various work that we might do together. And I was very pleased that he accepted our invitation to come and tell us about some of the work he's doing and how statistics might improve your lives, but you can infer that for yourself. So,
okay. Well, thank you for having me. Just a little bit about myself. This is my first year here at A&M. I'm coming from Berkeley, where I got my statistics PhD. I worked on a lot of astronomy, with a lot of astronomy data there. In particular, I was working with Josh Bloom's group, and they were studying how to classify periodic variable stars. So with modern surveys, we're collecting tens of thousands or hundreds of thousands of variable stars, and there isn't enough manpower to individually label each of these stars with a class, so we want sort of automated algorithms to do that for us. And an important part of that process of assigning a label to a variable star is estimating the period for a periodic variable. If you don't have the period, it's hard to do too much with the data. So sort of this, what I'll be talking about today sort of comes out of that research. So how do we do period estimation for variable stars? And in particular, I'll be talking about period estimation with multiband data and using correlations in phases and in amplitudes to try to improve period estimation. So this is joint work with Eric Chi and Richard Barn at Rice. So Eric is the postdoc of Richard's.
Are they in statistics or astronomy?
Eric got his PhD at Rice in statistics, and he's now a postdoc there. And Richard is a professor in, I think, electrical engineering. So yeah, we have a statistics heavy team. So hopefully, yeah, we get some good comments on our work here to the strongest side. Okay, so just a tiny bit of background about periodic variable stars. There are a number of reasons why periodic variables are important. One is for determining distances to clusters. So if we have a set of, say, Cepheids that are close to each other, we can estimate a period for all of those Cepheids. We can use the period luminosity relationship to determine the distance to that cluster or galaxy. And they're also, I think, periodic variables are used for estimating the Hubble constant. So in order to make much use of periodic variable stars, we need to be able to estimate a period for them. So here's a very well observed periodic variable from Ogle. So this star was observed over the course of about 10 years in the I band and in the V band. So the orange X's are I band magnitude measurements, and the blue circles are V band measurements on the right axis. And in order to really do too much with this, we want to estimate a period. So for this data, we have, for this star with this light curve, we have so much data it's quite easy to estimate the period. So the period is 2.48 days, and we can see if we plot the magnitude versus time modulo period, we can see the sort of the pattern of variation of sort of increasing and decreasing. And we can also notice particular quantities associated with this variation. In particular, the maximum amplitude occurs at about the same point in phase space, both the I and the V bands. And the amplitudes appear very similar in the I band and the V band. So this is potentially useful information if we're trying to estimate the period of a star. Okay, so for the light curve I showed you, estimating the period is easy. We had 700 measurements in I band and about 70 in V band, so a lot of methods are going to work well for finding the period. But there are a lot of data sets where it's much where things are much harder, where we have many fewer observations. So recently, McComas was trying to estimate periods, or was trying to find Cepheids. There were 9 measurements in the V band, 11 measurements in the I band. So a total of 20 measurements for 114 light curves. So there, it's much more challenging to determine this period. Another example, Cesar was doing a RLI research with SDSS data. So there are 5 bands of photometry, and they were fitting period algorithms only to the G band, so they were not using other bands of data, and they only selected light curves that had been observed at least 15 times in G, because they felt that because they felt they wouldn't be able to estimate a period with fewer than 15 observations. So we want to be able to estimate periods well in these situations where we have few observations per band, and we also want to make kind of use of all the bands of data for estimating periods. So that's what I'm going to kind of present today, an algorithm that can use several bands to estimate periods, and that's going to use a priori sort of known relationships between amplitudes and phases in different bands. So I think point 1 here is pretty clear. We want to use all bands. We have data in multiple bands. We want to use all bands to estimate the period. That's going to give us more accurate estimates. What do I mean by using known correlations in amplitudes and phases? So I took 100 well-observed oval type 2 Cepheids. So these have been observed at least 50 times in both I and V. And I estimated amplitudes and phases in the I and V bands. So these estimates should be very close to the true values because these are such well-observed stars. So the black point on this left plot, the black points are the amplitude estimates in the I band and amplitude estimates in V band. And there's a very clear relationship there. You don't see I bands with amplitude 0.1 and V band 0.4. That just doesn't happen. And we can use potentially we can use that knowledge if we have a new light curve. Say we're trying to find type 2 Cepheids. We have a new light curve. We're trying to estimate its period. Well, we have kind of constraints about what the amplitude should be in I and V band that we should incorporate into that period finding algorithm to make sure we have a very accurate algorithm. There's a similar story with phase. So phase is the point at which the light curve reaches its maximum brightness. And that point is very close, or usually is very close in both the I and the V bands. So the scale on this is a little strange. It runs from -3 or -pi to about pi. So -pi is saying that the light curve reached its maximum brightness at time modulo period 0. So basically, if you look at the folded light curve, this would be saying that the maximum brightness in the I band was right at the beginning of the folded light curve. The end here is saying that the maximum brightness in I band for the folded light curve is at the very end. And you can see that the point at which maximum brightness is reached in the 2 bands tends to be pretty close. So this blue line is I band phase equals V band phase, and most of these 100 Cepheids, they achieve their maximum brightness at a similar point in phase space. So we want to use this information.
Look at the outliers. I'm just curious what they are.
Yeah, so that's a good question. So there's some outliers here and here. So
Are they exactly 2 pi off?
Yeah,
that's what's going on, exactly. So these 4 and this guy, they're pseudo outliers. Because this phase is very similar to this phase, essentially. There are these points here are more legitimate outliers in the sense that their peaks are actually at a very different point in phase space. So that does
I thought we defined 0 phase as when it's at minimum or maximum, whichever you want.
Who's we?
We as astronomers.
Yeah, this is the decision.
Okay, so what you're saying is we make no derivation, or we have no assumption as to when the maximum or minimum happens. We just start folding.
Yes, that's how
Okay.
I'm defining. So I would say, as a statistician, that if the maximum in I band, the blue, or sorry, the red points, the orange points, that maximum is here as a phase of negative pi. The maximum is here as a phase of pi. And the maximum is here as a phase of 2 pi. But a phase of 2 pi and, a phase of pi and a phase of negative pi are the same, essentially. And as you get close, they become closer. So these points here and that point are not outliers. This is a kind of an outlier, outlier, outlier.
I'll say the peaks are the same between the two bands.
Okay, so we want to use this information in an algorithm. Okay, so it's sort of an outline for what the rest of this talk is going to be. I'll first introduce the Loam-Scargill algorithm for single band data. So the Loam-Scargill algorithm was created in, I think, the late 70s, early 80s by two astronomers, Loam and Scargill. And the original implementation was for single band data. I'll then talk about a very simple generalization that we can make to multiband data to try to incorporate any additional bands that we have. So this method, it's simple, it's very computationally fast. It's sort of the obvious extension of Loam-Scargill to multiband data. The problem is it doesn't incorporate any of these phase or amplitude constraints that we sort of know exist. So in the third part, I'll come up with a modification of Loam-Scargill for multiband data that does incorporate these phase and amplitude constraints. And that is kind of where the bulk of the talk is going to be. The fourth part of the talk, I'll address some sort of issues with the algorithm or sort of more details. There's a Bayesian interpretation for what we're doing here. There are tuning parameters in the algorithm that have to be chosen. I'll talk a little bit about choosing those. And this the algorithm is a bit more complicated than the simple Loam-Scargill, so there are computational issues, and I'll talk a little bit about how do we actually optimize the objective function. And then finally, in the last part of the talk, I'll apply this algorithm to some orbital to Cepheid curves. Okay, so Loam-Scargill for single band data. So let's start with some notation. We're thinking now about a single band. So we have measurements, brightness measurements, MI times TI, and in addition to the brightness measurements and magnitudes, we have error estimates, sigma I, on these magnitudes. So we can think of the data as being n triples, TI, MI, sigma I, and as the number of times we've observed this star. So what the Loam-Scargill algorithm does is it basically fits a sinusoid to the data. So a sinusoid has 4 parameters. There's a magnitude offset, beta, an amplitude A frequency, omega. So the primary emphasis here is to estimate the period correctly. The period is 2 pi divided by the frequency, so estimating the frequency correctly and the period, those are linked, basically the same challenge. And then rho is going to be the phase, so where we're seeing the maximum. So that's how I get the kind of weird negative pi to pi scale. It's coming from this function. And in general, we assume a normal measurement error with a mean zero and a variance sigma I squared. And sigma I squared is known, it's estimated in the process of collecting photometry.
So that is, I guess that's the statistician's way of saying that epsilon is not a parameter. You're just saying it's sort of the scatter that you expect when you fit the data.
So epsilon I is it's a random variable. So I get what this model is saying is that the light curve looks like a sine, and a magnitude measurement I get is the value of the sine wave at that time plus some error, and that error is normally distributed with variance sigma I squared. So the sine is sort of a crude approximation to the way these light curves.
Doesn't matter much. I mean, if you assume some other function with some other form, how closely approximated are the light curves with sine waves?
Yeah, so I'll talk about this a little bit. So certain classes are fairly well approximated by sinusoids. Other classes are much less well approximated by sinusoids. Your ability to estimate periods is somewhat related to how well the light curve.
Ah, I
It looks
see.
like a sinusoid.
Right.
So certain classes of variables give Lomscargle trouble. In particular, eclipsing binaries look very non-sinusoidal. You get basically two dips. And it's the kind of the best fit sinusoid to that. Doesn't fit
Oh,
very
yeah,
well.
right.
But even for classes that are somewhat non-sinusoidal, like RLI, you tend to get pretty good period recovery rates. So Lomscargle is popular in a lot of classification studies.
So in terms of the period, it does pretty well, at least for variable stars.
Yeah, so
Traditional.
what people do a lot of times is they use Lomscargle to estimate the period.
Right.
Then once you have the period, you look at the folded light curve, and then you use more sophisticated models with more tuning parameters to get a sense of the variation there. So you don't take the amplitude or the phase from the Lomscargle all that literally. What you do is you get the frequency, or you get the period using Lomscargle, and then you apply better algorithms to the folded light curve to estimate all sorts of things. So we have a model for the variation in magnitude. How do we actually compute these parameters? So the common approach that's taken is to grid the space of frequencies. So there's oftentimes a sort of known minimum and maximum frequency for the set of variables that you're trying to estimate periods for or frequencies for. So we grid the space of frequencies. And then at any particular frequency, we try to find the best fitting amplitude, phase, and magnitude offset. So when we compute the sum of squares difference between the magnitudes that we observe, the MI, and the model, A, sine, so on. So at any frequency, we get this what's called a residual sum of squares, and then we choose the frequency that best fits the data, that has the lowest residual sum of squares. So this goes on in part 3 here. I plotted the period versus the residual sum of squares in a particular period, and it looks like at about 2.5 days, that's where you have the best fit. And so you're going to, using the Lomscargle algorithm, you choose 2.5 days as the best fit period. So this is the sometimes known as the periodogram. Although the periodogram is inverted, but it has the same purpose.
Sorry, just curious, do you call that chi-square fitting in statistics? I just wonder if it's the language only strong.
Yeah, so it is like a chi-squared fit. I guess I wouldn't say that so much. Shenhua, would you
So we
say?
don't call it the chi-square fit. We would call it residual sum squares. That's the standard.
Yeah, so in statistics we call this a RSS, residual sum of squares, but
It's the same thing.
but
Please tell me it's the
Same.
But is that least square fitting?
so this, once you fix the frequency, you can find the best fit amplitude, phase, and magnitude offset through a least squares procedure. So this is at a particular frequency, this algorithm is very fast. So you basically run least squares, you find the three parameters, the amplitude, phase, and magnitude offset, and then you compute the residual sum of squares, and then you find the frequency, which has the minimum residual sum of squares. So I think, yeah, in astronomy, this is called chi-squared.
So when you treat these errors, are they, have you find that whether errors on A data, are those going to be correlated somehow to the frequency? Like the errors on the phase may be correlated to the frequency. So when you draw this diagram, you just get the best fit frequency for best fit number for the period.
Yes.
And that's not necessarily the best fit when you adjust the other parameters. What does that change? What change does that introduce to the best frequency? Or it doesn't matter. Suppose you get the phase off by a small number. How does that affect the frequency?
the fit for the
Yeah.
amplitude
Phase.
for phase.
The road, yeah.
So this residual sum of squares is at a particular period or particular frequency, and it's for the best for the best fitting amplitude at that frequency.
Anyway,
So yeah.
You're minimizing on all three parameters simultaneously.
Yes. Here you go.
so, but you don't marginalize on any nuisance parameters. But, you know, there are all the other parameters, you just don't care about the other parameters.
Yeah, so in practice, I think that once you have the period, you're going to, oftentimes you're going to fit a more complicated model to the folded light curve. I mean, you need the period or the frequency to fold the light curve. So you use Ohm's-Gargle, find the frequency, fold the light curve, and then come up with other parameters, sort of a more sophisticated model with
So,
more design
But
components.
my question is actually, so there's usually you don't marginalize the probability over, you know, all these other three parameters that you don't care.
I don't think
So I don't-
This is minimization,
Yeah,
right? You're
so-
saying
so
you're
I don't-
huge grid of A, rho, and beta.
No, I don't have a grid for
Oh, you
any
don't,
program.
sorry.
I just have a grid for the frequencies.
frequencies,
Once,
okay.
once I grid
Sorry.
frequencies, you
Sorry.
can get it's a closed form solution for the minimum A,
Right.
rho, and beta.
Yeah.
Which isn't obvious from this representation, but which you can find.
Oh.
In terms of other values, I don't have any priors on
Yeah,
A.
I mean, do you integrate over, because there is even though you minimize to A, for instance, but you know, there is still a range of possible A's. Do you
Yeah.
marginalize over
No,
that?
no, we don't do any marginalization.
Okay,
No.
that's what
And I mean, part of the reason for that is this procedure, we don't have a prior on any of the other parameters. This is a very frequentist procedure.
So you're just
so
looking
it's
for the
difficult.
absolute minimum. You're just looking for the absolute minimum.
Yeah, but this is maximum likelihood. This is a maximum likelihood procedure, or which is equivalent to minimizing the residual.
It's
sum.
minimizing the S group.
Okay, so just a quick review, sort of how Ohm's-Gargle was used in astronomy. So it's very popular for sort of a lot of classes of variable stars for estimating periods. Particularly popular in classification studies of periodic variables, because you're going to get a lot of different shapes, so you don't want to use template methods which just fit for RLI or just fit for Cepheids, because your purpose is classifying these. So you first run a Ohm's-Gargle, get a frequency or period estimate for a lot of stars, and then you can start classifying them as Myras or Cepheids or whatever. It tends to work pretty well even for at least somewhat non-sinusoidal shapes, although it does struggle. In particular, eclipsing binaries are a real problem. Oftentimes you estimate, I think, half the correct period. Okay, so let's move on to multiband data. So I'll first talk about some notation for multiband data, and then talk about the Ohm's-Gargle generalization for multiband data. And this notation, I think it makes a lot of sense to a statistician, but will be very complicated for astronomers. And the reason is because band B does not refer to like I, V, B. B is indexing the band, and capital B is the number of bands. So in general, we have two bands of data. In this talk, I'm only using two bands, I band and B band. So capital B is going to always be 2, because there are two bands. And then lowercase b is either going to be 1 or 2. So lowercase b equaling 1 is referring to I band data, and lowercase b equaling 2 is referring to B band data. So we have a set of times for a particular band. So those times are T, B, I. So this is the times in the Bth band. I indexes the number of times. Again, magnitudes associated with that time and magnitude errors. And then we have a certain number of measurements in the Bth band. So it's going to be NV. And then the data, it's similar to what we had before. We have triples, but those triples are for a particular time in a particular band. just as a kind of a review for this data, the capital B is going to be two bands. B equals 1 would be the ith band, B equals 2 is the B band. We have N1, that's the number of measurements in the I band, so there's a lot of I band measurements, 702. N2 is the number of measurements in B band, 76. And something like T215 would be the time of the 15th measurement in the B band. So I apologize for the B's.
It's all okay, just, I would say we use IJ instead of I guess.
Okay.
Yeah, that's what I
B is for band. that
Yeah, I
makes
thought
sense.
for a statistician that makes sense, but for an astronomer, they think it's the B of the band.
We get it, let's go.
You got it? Okay. Okay, so the simplest generalization of Ohm's gargle to several bands is just to say fit a sinusoid to each band separately. So we have, there are capital B equations here. And each equation is fitting a sinusoid to that particular band. The frequency of the sinusoid we want to keep fixed for all bands because we're going to have the same frequency across bands. But the magnitude offsets, amplitudes, and phases we're just going to allow to be anything they want to be with the different bands. And then we can do a similar procedure to Ohm's gargle with grid frequency space. And then at any particular frequency, we do a chi-squared fit, but now we have to do it across all times in each band. So there's two sums here. And then we're going to choose the frequency that minimizes this residual sum of squares with this chi-squared fit. So there's no effort is made to keep amplitudes or phases similar in the different bands. So it's clearly we're not using all the information we have. Okay, so as an experiment with Ogle data, I took 100 type 2 classical Cepheids, and I downsampled them so that they're originally very well sampled, like 100 measurements per band. I downsampled them to 10 observations per band. And then I estimated periods using the algorithm on the last slide. So fit a separate sinusoid to each band with the same frequency for each sinusoid, but allowing all other parameters to be completely free. The result is that you get about a third of period estimates are wrong, which is sort of unfortunate. You'd like to have a higher accuracy.
Do you use unsample randomly, or do you follow any?
I truncated. So there's a lot of ways you could. So I just took the first 10 measurements in each band. You could also thin, so you get 10 per band. So now let's take a look. So we got the 34% of these Cepheids. We got the period incorrect. We're more than 5% off the period. What are these best fit phases and amplitudes? So here are the best fit phases. So on the left, this is for the downsampled Cepheid light curve. So there's only 10 measurements per band here. And on the x-axis is I-band phase, and on the y-axis is V-band phase. And you'll notice that a lot of these phase estimates are inherently unrealistic. So you get phase estimates of 0.8 and negative 2.8. And you knew before you started estimating the phases here that this is really not a realistic estimate. And in particular, so the points are colored, and the point type is based on whether the period estimate was correct or incorrect. So you can see that a lot of the light curves where you got the incorrect period, their phases are very unrealistic. So the correct periods tend to be along the line, and the incorrect periods tend to be away from the line.
You're correct, you get within 5% of the
Within 5% of the full point. I mean, you can compare this, like these are for the full light curves, you never get, say, phases around here, but you get a bunch here. So potentially by incorporating constraints on phases that we sort of know about from existing data, we can improve estimation of the period. So we constrain the phases, that's going to help us with periods. A similar story for amplitudes. There are a lot of unrealistic amplitude estimates here. And we sort of know that we shouldn't be getting anything in those areas. So we want to incorporate some constraint on amplitudes into this algorithm. Okay, so how do we do that? So the way I think a lot of statisticians would approach this problem is by modifying the function we're minimizing to include a penalty. So originally, with the algorithm I posed a few slides ago, the multiband Monte-Scargo, we just had this residual sum of squares. We're just doing a best fit sinusoid to each band completely independently. What we're going to do now is we're going to add penalty terms, and those penalty terms are going to try to force the phases, rho, and amplitudes A to be near values where we expect them to be near. So we want these functions, J rho and JA, to be large when rho and A are unrealistic, when they're far from what we expect them to be, and we want these functions J rho and JA to be small for very plausible values of phase and amplitude. So for example, equal phases in the two bands are very plausible. We see that a lot. So if the phases are equal in I and D, then we want J of rho to be 0. So PNLL, that stands for penalized negative log likelihood. So this is the negative log likelihood, and this is the penalty term. So then finally, along with these sort of astronomical considerations for J rho and JA, we also want to produce an algorithm that's computationally fast. You don't want to propose having some penalty terms that are just impossible to find a minimum here.
So is this what you would call the prior or not?
So I will talk about that in a few more slides. The motivation for this is not based on really a prior. This is the penalized likelihood method, but you can interpret what we're doing here as a prior.
As a kind of prior.
Yes.
Okay.
So this is sort of a frequentist method, penalized likelihood methods, but there's a Bayesian interpretation involving priors to what we're doing here. So that the algorithm that we come up with can be motivated either through frequentist or through Bayesian considerations, and if you're Bayesian, then you're going to have a prior. And the J rho and J A will be elements in that prior.
Philosophically, they're similar in frequentism. Like, would they be insulted if I said that? Because, I mean, so there's a log likelihood. You know, so those are just probability terms. The penalty terms are some knowledge a priori of the distributions of rho and A. Or is that,
Well,
did I just say something sacrilegious to
Yes.
Okay.
yeah, I mean, there's a very close relationship. In
Right.
fact, what we're doing, this is a penalized likelihood method. It's going to also be a Bayesian maximum a posteriori estimate. Sort of like almost why you're doing it is
Right.
whether it's frequentist or Bayesian rather than the results you get.
Right, okay.
Okay, I have a silly question. What's the difference? I mean, it seems like it's very distinct, frequentist versus Bayesian. What does that mean to me? I honestly, it's
So-
like the bourgeois versus the proletariat. I mean, I don't understand.
No, actually, we can forget about this debate between the Bayesian and the frequentist because it can take a whole day. So I suggest we just move on.
Okay.
This is just one method which makes sense, right? So you have the first criterion, and then because of some observations James had, so it's nature to assume, oh, they are very close. So you add a penalty to force them to be true. So it's very nature. So I think if you accept this is nature idea, we can just go on. Right? So move on, please.
Yeah, this frequentist and Bayesian is, if you talk to particle physicists, that's all they do. They argue on this for their entire life.
So we don't want to go down that road.
So we can use all the rest time to debate. So let's
Yeah.
forget about it. So let's look
Yeah,
at the
okay.
good results.
Let's keep it an astronomy seminar.
All right, so in the next few slides, I'm going to talk about specifically how we choose what J rho and JA are. What are the penalty terms? So I'll start with the J rho, which is a bit simpler. So I'm going to define rho bar to be the average phase across B bands. And the penalty that we're going to use is going to take the square difference between the phase and a particular band and the average phase. So this rho b minus rho bar squared is going to be large when rho b is far away from the average phase. And it's going to be small if rho b is close to the average phase. This gamma 1 is going to control how much we want to force the phases to be similar. So if we set gamma 1 to be very, very large, we're going to basically make it so that the phases have to be the same in every band. And if we set gamma 1 to be smaller, we're going to allow for more scatter across phases. And if we set gamma 1 to be 0, then we just go back to what we were doing before, because in that case, J rho was just equal to 0. So this middle term is the more intuitive understanding of the penalty. The representation on the right here allows us to think of this as a projection. So essentially what this penalty is doing is go back to the so here the phase estimates. Say I have a phase estimate that's here. I can decompose that into the phase along this blue line and then the phase coming out here. And then I want to penalize for large values that are orthogonal to this blue line. In fact, so what this, just see it clearer here, this is just taking the squared norm of the vector that's orthogonal to the blue line. And I'll talk more about how we choose gamma 1 later. But that's these algorithms, when you sort of use a penalized likelihood method, there are sort of more things you have to tune and more computational considerations that we'll talk. Okay, so what about for JA? We want to penalize for unrealistic values of the amplitudes. So one thing we could do is take the same approach as we did for the phases. So we could let A bar just be the average of the amplitudes across the B bands, and then penalize cases where the amplitude in the particular band B is far from the average amplitude. So that's what I originally did, and after talking with Lucas, I realized that that was a bad idea. And the explanation for why it's a bad idea is pretty simple. So it's sort of explained by this plot. I took 100 R Lyrae from Ogle. These are well-observed light curves, so we can estimate the amplitudes in the I band and V band quite well. And you can see that the amplitude estimates fall roughly on this blue line. And this blue line is not I band amplitude equals V band amplitude. That's the black line is I band amplitude equals V band amplitude. So if we use this penalty here, we're going to be pushing amplitude estimates towards this black line, which is definitely a bad idea, especially for RLI. If you had a class of variable stars where you expected the amplitudes in I and V band to be similar, that might be a good idea to push towards the black line. But we don't want to do that for this case. We want to push towards this blue line. So the penalty that we use is going to do that. So it's a little bit more complicated than the penalty on the phases. And the way we can choose this penalty, so say we're trying to estimate periods for R Lyrae. Take a bunch of well-observed R Lyrae curves, light curves, say n well-observed R Lyrae light curves, estimate amplitudes for each of them. These amplitude estimates should be roughly correct. We're going to let A tilde be the average amplitude, but with norm 1. So A tilde for this data is going to be somewhere along this blue line. The red dot is the average amplitude. A tilde is a normalized version of this average amplitude, so it'll actually be more out here. And then this penalty, which has a somewhat similar form to the rho penalty is going to push amplitudes A towards the A tilde vector. So the interpretation is the same for a amplitude here. You decompose this into an amplitude along this blue line and an amplitude away from the blue line that's orthogonal to it. And then we're penalizing this vector, the norm of this vector squared. That's what JA is. And then again, gamma 2 is going to control exactly how much we're going to force the amplitudes to be close to that blue line. So if we like gamma 2 be very high, we're going to push all amplitudes to be like right on that line. And if we like gamma 2 be smaller, the amplitudes can have more scatter. And we could like gamma 2 be 0, and then we won't be trying to force the amplitudes towards any point. Okay, so just to summarize, we have this penalized negative log likelihood, which was composed of fitting each sinusoid separately to the bands, and then penalty terms to try to force the phases and the amplitudes to be where we think they should be. So there's a bunch of kind of remaining issues here that I'm only going to get a chance to talk about very briefly. So I'll talk about a Bayesian interpretation to what we're doing, how we choose gamma 1 and gamma 2. That ended up being kind of tricky. And then how do we actually compute this penalized negative log likelihood? So I proposed a function. I say, well, we want to find the omega that minimizes this. But it's like, well, how do I do that? So we have an algorithm for doing that that's pretty fast. Okay, so just
James, can I give a suggestion? So
Yes.
can you talk about the Bayesian and last, talk about other component first? So
Okay.
I think that'd be better,
Okay.
maybe.
Sure, well,
No, this is very confusing. Yeah, so that's,
anyways, you can think of this
Yeah,
as
skip
being
this
Bayesian.
part, yeah, so we come back later. So yeah, this is more important because we know this, we know how to do it, right?
Yeah.
So we want to know how
Yeah.
to do it first and before.
Yeah, I mean, I agree. I don't think it's all that important whether you think of it as
right.
frequent distribution.
Yeah, yeah.
You can do it with whichever way.
Right.
It does actually help a bit with choosing gamma 1 and gamma 2 if you have a Bayesian interpretation. Okay, so very briefly in one slide, how do we choose gamma 1 and gamma 2? So I'll just talk about choosing gamma 2. The principle is similar for choosing gamma 1. So we have a amplitude estimates in I and B band for a bunch of well-observed light curves. We have this A tilde, which is this blue line. Basically, we're going to choose gamma 2 proportional to the scatter of the amplitudes around this blue line. So for well-observed light curves, we often see amplitudes that are pretty far from the blue line. We don't want to push amplitudes too much towards the blue line, towards the average amplitude in I band and B band. However, for well-observed light curves, alternatively, for well-observed light curves, we see that they're very tightly along the average line, then we're going to want to push more strongly. So just roughly, gamma 2 is chosen proportional to the scatter of amplitudes around the blue line. So these, the two red lines are the standard deviation of the measurements going out from the blue, and then the gamma 2 is proportional to the square of the difference between the red line and the blue line. That's the intuition. It has, there's some tricky statistical issues behind this that I don't fully understand, so we're still working on ways to choose gamma 1 and gamma 2. But that's roughly what we're using there. Okay, so some issues with computation. So if we're just fitting these sinusoids separately, things are quite fast. So minimizing the residual sum of squares for a particular omega is just a linear regression with 3 predictor variables. So if you do that quite quickly, computing the penalized negative log likelihood turns out to be quite a bit slower. There's no closed form solution. So our approach, Eric Chi, my collaborator, is an expert with minimizing algorithms, so a lot of his work has gone into this part. This is actually a much bigger part, should be a much bigger part of the presentation. But we iteratively minimize with respect to rho A and the magnitude offsets. Updating with respect to the amplitudes and the magnitude offsets is actually pretty quick. So there's a closed form solution for that. Updating the phases is trickier, and our current algorithm is using a majorization minimization. It turns out that fortunately, we don't actually have to compute the penalized negative log likelihood for every omega in the grid, so for every possible frequency. And basically what you can do is you compute the residual sum of squares for every frequency. And then a lot of these frequencies look really bad with just the residual sum of squares. And you basically know that this frequency is not going to minimize the penalized negative log likelihood. So we might have a grid with 10,000 frequencies, but we tend to only have to actually test maybe 50 or 100 frequencies for the penalized negative log likelihood. So you're not minimizing the penalized negative log likelihood for 10,000 frequencies. You're only doing it for like a couple hundred. And then we're working on an R package called Multiband for doing this. So we're hoping to release it once we have a paper together. Okay, so just some testing with Ogle data. So I took about 100 type 2 Cepheids from Ogle. We downsampled them. So originally these light curves have 50 to 100, or at least 50 measurements per band, but we downsampled them. So we get to 5, 10, 15, 20, and 25 measurements per band. So we get 5 sets of light curves. There's 100 light curves per set, varying quality, starting with very, very poorly sampled light curves, only 5 measurements per band, and up to decently well sampled light curves, 25 measurements per band. And then we ran the Lomskargel without the penalty on each of these 5 sets, and the Lomskargel with the penalty. And we consider a period estimate to be correct if it's within 5% of its true value. It's very heuristic. 5% doesn't have much. So what we get, so here I plotted, we have a table for each set of light curves. So there are 100 light curves in each of these sets. The fraction of times we get the period right with just the residual sum of squares method, and a fraction of time we get the period correct with the penalized likelihood method. And we have decent gains in accuracy for very poorly sampled light curves, such as 5 observations per band and 10 observations per band. Once we're getting up to 20 and 25 observations per band, the methods are returning a similar performance. So it doesn't seem like, if you have well-observed light curves, it doesn't seem like this method is giving you much. And that makes sense, that once you have a lot of data, the data is going to, the residual sum of squares portion of the penalized negative log likelihood is just going to dominate, and the penalties are going to be, the order of the penalties will be very small.
Bayesian would say the data will overwhelm the prior.
Yes, exactly. And then this table's slightly unfair statistically because I use the 100 Cepheids to learn A tilde, gamma 1, and gamma 2. So you should have separate sets of data to do the tests, to learn the parameters and to actually test. I don't think that's being all that optimistic towards the penalized negative log likelihood method. Okay, and then just very briefly, I'll go through a bunch of results. So here are for phases with the 5 observations per band. On the left, you get the phases that the residual sum of squares method is estimating, and on the right, the penalized negative log likelihood method. So with 5 observations per band, the residual sum of squared method is not trying to make the phases equal in the different bands. The phase estimates are just all over the place. And for the penalized negative log likelihood method, the phases are right on the line. That's because there isn't much data, so the phases kind of go to where the penalty is telling them to go, or where the prior is telling them to go, and the prior is telling them to go to the line. I band phase equals the end phase. So we can make this for 5 observations per band, 10, 15, 20, 25. So here's with 10 observations per band. You'll notice that there's less scatter for the RSS method here, but more scatter for penalized negative log likelihood. And then as you get 15, 20, and 25 observations per band, more and more scatter for the penalized negative log likelihood. Basically, the prior or the penalty term is being washed out by the data as you're getting more data, and so the phases are moving away from where they're pushed to be. And the residual sum square method, the phases are now concentrating on the high band. And it's a similar story for amplitudes with 5 observations per band, residual sum squares method, which is not constraining amplitudes at all. They're sort of all over the place, whereas the amplitudes for the penalized negative log likelihood method are right where you're telling them to go. And then as you get more observations per band, there's more and more scatter for the penalized negative log likelihood and sort of less scatter for the residual sum squares method.
I'm confused a little bit with the table you showed then, just in terms of the improvement. Because here it looks like the improvement is very drastic, but that's just a visual.
Well, just because you're getting,
So you see that there's a lot of incorrect period in that line. Was
Yeah.
that all?
Okay.
So still incorrect?
yeah, so it's estimating realistic, what this plot is saying is that the penalized negative log likelihood method is estimating realistic phases in the sense that the phases are close in both I band and V band.
But
But
they're
it doesn't mean that that doesn't mean that you're even getting the correct phase.
They're outside of the 5% of what you get with the full data size, which is so there was a 5% off from whatever you have when you have 100 observations instead of 5.
The frequency is.
The frequency is,
Yeah.
right.
So, I mean, just because a point lies on this line, it doesn't even mean you have the right phase. The actual phase could be out here.
Right. Then going to the higher, the larger number, this one I think, but here even, so there's more triangles, okay. Well, I mean,
There are fewer triangles, so you're getting
there are
more
triangles than
more
what I
correct.
expected, they're all correct. You should read my mind.
Okay, so when we look at the theories, we should look at whether or not there are fewer or more red triangles versus they all land on the line or not.
Well, the red triangles are just, I mean, you can get that information from this table.
Right.
The fraction of the
That's right.
observations that are red triangles, that's the fraction of incorrect observations. So, or, sorry, incorrect observations, incorrect period estimates. So that's given by this table. So basically, with very poorly sampled light curves, you get a bit of a benefit in estimating periods correctly. 6%. With 10 observations, you get a pretty big jump. Then after that, it gets pretty close to being the same between the methods. We sort of expect that to happen somewhere. So the purpose of having red triangles and black circles here is more to say, like say in this plot, you can tell that the times when the I band phase and V band phase are estimated to be very different, you often have red triangles, whereas when the I band phase and V band phase are similar, then you have more black circles. You're more likely to get the period correct. Okay, so just to wrap up, what I propose is by no means the only method to estimate periods for multiband light curves, so I don't want to make it seem like this is totally new by any means. So there's a lot of template fitting methods for multiband data. So basically you take a set of well-observed light curves, construct templates, and then given a new light curve, you try to match it to one of your templates. And then there's methods for combining bands. So if you get measurements in each band at the same time, you can try to create sort of a super band which has minimum photometric error. And that is a method by Subijis which uses principal components analysis to do that. And then just to kind of wrap up with some current problems and future work. So there are some interesting statistical issues with choosing these tuning parameters, gamma 1 and gamma 2. I'm working on that now. It's quite tricky. I did some initial tests. The test with the Cepheids that I showed you at least turned out decently well. It looked like the penalized negative log likelihood method was improving period estimation accuracy. for when you have very poorly sampled light curves. I did some tests with RLIR, it worked terribly. I don't know why that is. Could it be that RLIR are more non-sinusoidal than Cepheids? Maybe I'm not selecting gamma 1 and gamma 2 in a good way. I'm not sure. So the method is still sort of in the proto-development phase. And then the sort of the situation where this method would be optimal, kind of the optimal data set, would be you have a lot of bands, but very few observations per band. So I would like to test this for a situation where you have, say, 5 bands of data and 5 observations per band. So in that case, you have a total of 25 measurements, but you have 16 parameters, because you have 3, you have an amplitude, a phase, and a magnitude offset for each band. So 3 times 5, 15, and then you have a frequency. So you have 16 parameters, but only 25 measurements. It's going to be very hard without having a prior or having a penalty to get good estimates on those parameters. So as the number of bands increases, but you keep the observations per band small, I think that's the situation where this algorithm is going to have the kind of best performance relative to not having penalties. Okay, so I think that's it. Thanks. Go. Questions?
So in all of the, say, 10 observations, and you have 100 light curves, do you pick a gamma 1 and gamma 2 and leave them fixed for all 100 light curves, or can you adjust them as you run through them?
Yeah, so I'm keeping them fixed for all light curves. I think the decision about whether to fix or change will be based a bit on what, if you're targeting specific classes. So say you're looking to estimate periods for RLIR, then you'd want to choose a different A tilde than for Cepheids. And you might want to choose different gammas than for Cepheids. So I think if you're doing a hunt for periods for Cepheids, then I think keeping those fixed for every light curve you're applying the method to. But if you want to target different sets of variables, you potentially want to change the gamma 1 and gamma 2.
So you derived gamma 1 and gamma 2 from the data itself, and typically you would want to derive, I guess what was called a prior, sorry. You'd want to derive the prior not from your own data, from some other source of data. So my question is, if you were doing some other application of this, how would you know what prior function to choose if you're doing some new project where you don't know the relation? You don't know that there's a relation between I and
So if you're doing something where you don't know there's a relationship between I and V band, you're going to, I think, have trouble. Yeah, I mean, it's going to be difficult to use the penalized negative log likelihood. I mean, if you think you may think that, for example, you don't have a relationship between the amplitudes, but you do between the phases, then you can turn off the amplitude component.
I think the question is more like we say, is that gamma 1 and gamma 2 is related to the photometry error of that specific observation? So if you say you got this gamma 1 and gamma 2 from your old survey, can we use the same gamma and gamma 2 for the type 2 Cepheids in the other survey that has less observations?
So you don't want to choose gamma 1 and gamma 2 based on photometric error. What you want is
But the photometric error already in there. They're in the RSS chart. Right?
Okay.
what you want is, so say you have a new a bunch of light curves from a new survey that's some say photometric error, and trying to find periods for Cepheids. You have some prior knowledge based on previous surveys what the distribution of amplitudes is for Cepheids. And these amplitude estimates are very close to correct because these were very well observed light curves in oval. You would then want to use this data to estimate gamma 1 or to estimate gamma 2. but you don't want to incorporate photometric error
So you can use
into that.
the gamma one and gamma two derived from this observing and apply that value to the other observations.
Yes, it shouldn't, gamma 2 shouldn't depend on photometric error. What it would depend on is if for the new survey, if you thought there was going to be a different relationship between I-band amplitudes and V-band
Okay,
amplitudes.
so if
So
it's,
if you're,
it's a different band, then it matters, but if the same filter set, it should be the same.
Because that's dictated by physics.
Yeah,
When it has to
Okay.
yeah.
stellar atmospheres.
yeah, so that's.
Yeah, I still.
You do, okay.
It's-
You have to
it's-
teach, and you all have a free lunch on the 5th floor, so we should call you.
No more questions.
Ting has a question.
I have last question,
Wow.
but I asked it in the-
Anybody else? Last question, Ting,
Okay.
yeah.
So, my question is why when you start with this penalty thing, why you don't say, I force the phase to be the same for two band, and I force the amplitude to be same but just different by constant. Did you try that and see what you get?
So there's a couple of reasons to not do that. One is the phases, they're not the same in different bands. In fact, if you look at, you can see it. Sorry. So this is for Cepheid data, these are the phases. The phase in V band tends to be kind of an offset. It's actually ahead of I band.
And that's again physics.
Yeah, so I mean, this penalty that we're using is kind of an approximation. We're forcing them to be they're similar.
Yeah, because if you look at your final result with like 5 observing with the penalty
Yeah.
method, you kind of the same way that you force them to be kind of like the same.
Well, there's so little data in that case that when you minimize this penalized negative log likelihood, you effectively, the estimates just go to where that minimum is, J rho. You could say gamma, if you want the phases to be exactly equal in your estimates in the different bands, you should just set gamma 1 to be very large, and it'll do that.
But I'm just curious if you run that to force the phase the same and the amplitude to be same but differ by a constant, run these, what's
Yeah.
actually, you can make another column
Yeah.
in that table and see what's the completeness you get.
Okay, so just you're saying run the algorithm with gamma 1 and gamma 2 very high. Yeah, I think that would do it. Yeah, I mean, I think, yeah, that's interesting.
No.
It depends on the grad students, because you're just keeping them from lunch at this point.
Yeah.
You can, we're gonna let them go to lunch on the third. All right, let's thank James again.